All right, I want to talk a little bit about J and K integrals. See if we can make sense of when they arise, why they arise, and how they might affect the energy. So we're going to make this real simple. It's just two electron systems. They will be Hartree-Fock type systems for now, which means that there are two electron Slater determinant. I've written it in shorthand here such that I'm really only showing you the diagonal elements here. Of course, it would look like chi1 electron 1, chi2 electron 1, chi1 electron 2, chi2 electron 2 here for the full determinant. You'll see it written out in a minute. What we mean by chi I is spin orbital I. So it's got a spatial part, as you've seen here. For example, chi1 is a 1s orbital, so that would be spherically symmetric, times an alpha spin function. We need to specify all the coordinates of the electron, and spin is one of those coordinates. We'll designate electron 1 being in that orbital as 1s alpha 1. Now, I know there's no R1 here, but that's implied. And so electron 1 has three spatial coordinates and a spin coordinate, which we've picked as alpha. And just to remind you, for fermion electrons as fermions, there are two spin functions, alpha and beta. We actually have no idea what the functions are. We have no idea what the internal coordinates are. It doesn't matter. They're an angular momentum. So we know that the functions can be normalized and they are orthogonal. So we would say they're orthonormal. And since it's an angular momentum with quantum number a half, S squared on alpha gives us 3/4 h bar squared alpha. Same is true of beta. Sz, that is the Z component of the angular momentum of the electron in the alpha state is h bar over 2, beta it's minus h bar over 2. And so if we take this Slater determinant, multiply it out, whatever chi1 and whatever chi2 are, it has this form. And we said in the last video that the way we're going to evaluate the energy was to take the expectation value of the Hamiltonian. So that's what I'm doing here. Phi star, electron 1 and 2, H, phi 1 and 2. And then I'm cheating here. I'm just saying d tau 1 and d tau 2, and I don't know why I put that parentheses here. By the way, I should mention that on the Google Drive, anytime I use either a PowerPoint or a PDF like that, like this, it is stored on the Google Drive. So if you're going to go back and look at it, you can. I know my handwriting's not great, but maybe it's useful. All right, so I have to evaluate this. And if you look in Szabo and Oxford, section 2.3.3, there's a set of rules there called the Slater-Condon rules that show you how to evaluate. I would be happy to work with anybody who's interested in it, but doing it in this video format would be more than lethal. So I'm just going to say, here's what you get. In general, you will get a 1 electron Hamiltonian, so it's kinetic energy and attraction to the nucleus for electron 1. For orbital 1. You get the same for orbital 2. You'll get an electron, classical electron repulsion between electrons 1 and 2. And then, in principle, we can always write this term. You're going to see in some cases K12 is 0. And it will be 0 when spin orbital 1 and spin orbital 2 have different spins, alpha, beta. All right, so here's HII written out in terms of spin orbitals. It's the little 1 electron Hamiltonian, kinetic energy attraction nucleus, and orbital 1, which I have designated above as 1s alpha. They both get complex conjugated. 1s alpha, and now I'm going to integrate over the spatial coordinates and the spin coordinates. And we saw above that alpha star times alpha integrated over all spin space is 1. That's what I mean here. I'm sorry, this line should have come over here to designate that alpha. Since the Hamiltonian here does not depend on spin, we can pull that integral out and get a 1, and then all we get is this spatial piece. 1s, h, 1s. Attraction, nucleus, and kinetic energy. As we saw in the previous video, J12 is just a classical repulsion between an electron in orbital 1, spin orbital 1, and spin orbital 2, and there's the R12. And here, for one of the very few times I've written in MKS units, because that's what you're familiar with, atomic units gets rid of the E squared, gets rid of the 4 pi epsilon naught. You can convert between them. So what does this integral look like? Well, here's a charge distribution. It's like a blob, right? We have some electron in chi1, and it's spread out over all space. But if it's separate from chi2, it's pretty easy to see what you're doing here. You're picking a value of R1, and therefore chi1 has some value in that region. Picking a value of R2, and so you're picking a value in that region. And then you're going to integrate, and the repulsion goes as 1 over the distance between them. And then the red is meant to indicate that you're just going to do that for all possible positions of R1 and positions of R2. Now, I didn't mention spin, but since chi1 has, in our case, alpha spin, I can integrate out the spin part here. It'll be alpha star times alpha. And in principle, chi2 has some spin, but it will be its spin complex conjugated times its spin. I can integrate out the spin part, and this really becomes an integral over of classical repulsions between charged densities. But K is weirder. Here's chi1 star chi2 for electron 1. So now I've overlapped these charge densities. Here's the orbitals. Here's chi1. Here's chi2. And we're going to pick R1 and then multiply chi1 times chi2, and I get a value right there at R1. We're going to do the same thing at R2. We're going to pick R2, multiply chi1 times chi2, and we're going to go over all space. But look at this. If chi2 and chi1 had different spins, let's say chi2 was beta spin, chi1 was alpha spin. It wouldn't matter what the rest of this was. When I did the spin integral, I'd get something that looks like this, alpha star times beta, or beta star times alpha. And since the electron repulsion does not depend on spin variables, you can pull this integral out, we do it. So what that means is K integrals go away when the two spin orbitals have different spins, but they don't when they have like spins. So let's see what that means. If I put two electrons in a 1s orbital, one with alpha spin and one with beta spin, I'll get two H1s1s, that is the energy of the 1s orbital, because they're both in the same orbital, and I'll get a repulsion term. Now that may seem a little puzzling, but there's two electrons in that 1s orbital, and they do repel one another, this is how you calculate. But there's no K because they're of opposite spin. So another possibility would have been to say, forget Pauli. I'm going to put two electrons in a 1s orbital with alpha spin. There's your determinant. You got two columns that are identical. This wave function is identically zero. That's the Pauli principle at play. You can put at most two electrons in an orbital, one up spin, one down spin. There's another possibility. I want alpha spins, but they're going to have to be in different orbitals. It's 1s, 2s. Write it out. Now I get an energy term associated with an electron or 1s, a one electron term associated with an electron at 2s, the repulsion between electrons in these different orbitals now, and a term that comes minus K 1s 2s. Now remember, it's not as if electron 1 is in the 1s and 2 in the 2s when you have an exchange term. They're sort of exchanged, so they're both. Nevertheless, you get an energy term here, and that energy term, K, is always positive, but if it comes with a minus sign here, it lowers the energy. How do we understand it? Well, one way to understand it is to write out the wave function. 1s alpha 1, 2s alpha 2, minus 2s alpha 1, 1s alpha 2. When it's the case that the two electrons' spatial coordinates are identical, you've got 1s, let's call it R. You've got 1s R, 2s R, alpha alpha, minus 2s R, 1s R, alpha alpha. And order makes no difference on the multiplication here if the variable is the same. So you get a wave function that goes to 0 when the two electrons end up on top of one another. When I have two spin up particles, the wave function goes to 0 when they get on top of one another. But that's interesting. That's the biggest repulsion you could get. The repulsion goes to plus infinity there. This wave function throws that out. It says they can't be on top of one another. And so that's how we might understand this lowered electron repulsion due to like spin particles. If instead you had written 1s alpha, 2s beta, so it's still one electron to 1s, one to 2s, but with different spins, you get an energy term that looks like this. If the spatial orbitals are the same, this term would be the same as the above. This term would be the same as below. The repulsion would be the same in both cases classically, but there's no exchange term. And what you can show is that this wave function does not go to zero when the particles get on top of one another. It's 1sr1, 2sr2, but here it's alpha 1, beta 2, here it's beta 1, alpha 2. Those are different functions. You know, we don't know the internal coordinates. So what it says is like spin particles have lowered repulsion due to the exchange interaction, due to that beast right there. And it's going to be important for us to get that right.